Maybe. I don't know. I don't care very well because I wasn't here last year. Which page?
Oh, it's just the stuff of other time. I'm writing.
Good. Everybody brings lots.
Okay, so we're going to talk about sigma notation because this is going to come in to play when we're moving towards finding exact area under the curve. And just like with limit definition of a derivative, we're going to have to do something that feels a lot more tedious to begin with. And then once we understand that concept, then we'll move into a much more efficient way of finding antiderivatives. But there is, limit definition of area is presented in some sort of way on the AP exam. So I'll show you what that looks like. But let's start off with this. Sigma notation. All this means is it's an indication for us to show that we want to add a bunch of terms together, and allows us to represent in a formula form instead of writing out all the terms one by one. So if I have a summation, that sigma just indicates I'm adding a bunch of terms together. I'm adding a bunch of a sub I terms, and my index indicates the variable that I'm going to be kind of plugging in. Lower bound is always the smallest value that I plug into my expression, and that summation just means I'm going to continually add every term until I reach my upper bound. That's going to be my final I value that I plug in. So in this case, we're going to start off with a sub 2 because that's the lower bound. Next up, we always increment by 1. So next is a sub 3, and then plus a sub 4, and we keep going until a sub 5. Now that 5 doesn't mean that there are 5 terms necessarily. That just means that that's the last term that we plug in. And because we start with 2, there's only 4 terms, right? A sub 2, a sub 3, a sub 4, a sub 5. So see if you guys can try example 1. We want to find the summation of I squared plus 1 from 2 to 4. So if I plug 2 into my expression, I'll get 2 squared plus 1. And then my next value is 3, because I'm always going to increment from my lower bound to my next integer value. 3 gets inserted, enter that into our rule of sequence, our formula rule. Then 4, and we stop at 4. Yeah. Now, we do have some shortcut rules for certain summations. And let's say I wanted to add 1 plus 1 plus 1 all the way to n. then the shortcut is that's just n, right? Whatever my upper bound is, it's always going to be n. Now, all these summation rules start with a lower bound of 1. Okay, so this only works if we're going from starting with 1. The second rule says, what if I have summation of I starting with 1? So 1 plus 2 plus 3 plus 4 plus 5, all the way to n, whatever the n value is. Rather than adding all those terms up one by one, the shortcut is take the upper bound, multiply by one value above the upper bound, divide it by 2, and that will be the sum, rather than adding up 1 plus 2 plus 3 all the way to whatever that n value is. Okay. Next up, summation I squared. So this one will be 1 squared plus 2 squared plus 3 squared plus 4 squared. Rather than adding up all those terms, the formula is take the upper bound. Let's say that upper bound was 10. Then it'll be 10 times 11 times 21 divided by 6. That will give us the sum rather than adding all these up. Summation I cubed follows with another rule here. And the fifth rule says, if I have a coefficient that is part of my summation, I can pull that coefficient out and then just multiply that coefficient with the summation. So sometimes that coefficient in front will make it so that we don't have to look at that coefficient, it doesn't interfere with our rule. Visually, feels a little bit easier to work with if we can kind of separate the parts that we got to deal with and the parts that we don't need to worry about. Okay, let's look at some examples here. I want to take advantage of the rules here. So summation from 1 to 8, I don't want to have to add all these terms up to 8. So I want to take advantage of the summation rules above. What we can do is, with that plus sign, we can think of this as the sum of 2 separate terms. So, and as I do that, I'm also going to pull the 3 out in front. So 3 summation from 1 to 8 of I squared plus, and I'm also going to pull the 2 out in front as well. If I pull the 2 out in front, then I can just make this summation 1. And if I can represent my summation using the rules, then I can just replace these with the rules that I have above me. So we know summation of I squared is just going to be n times n plus 1 times 2n plus 1 all over 6. What's my n value that I can use?
8.
8, yep. So 8 times 9 times 17 all over 6. Take that number, multiply by 3. And in here, my summation is summation 1, so my rule is just n. So this is just going to be 8 times 2, which is 16. Okay, we can use our calculator here. For example 3, we would like to apply the summation rules, but that parentheses squared is kind of getting in the way. So we're going to FOIL this out. Once we get them all separated, then we can start matching the rules that we can use. So we can think of this as summation of I squared plus 4i plus 4. And then we can separate each and let each have its own rule that we can apply. Let me use a space above here because I might run out of room. So I'm going to say summation I squared. We have a rule for that. Plus pull the 4 out, summation I. I got a rule for summation I. And if I pull the 4 out for the last one, I also have a rule for summation 1. So I definitely have a rule that I can apply here. I got a rule that I can apply here and a rule that I can apply here. And the coefficients can just multiply to whatever the sum I found in each region here. This one is just going to be 10 times 11 times 21. This is just 4 times 10 times 11 for 2. And then summation 1 is just going to be n, just 10. Example 4, this looks a little bit strange because we see a bunch of k's here. But here, my index variable is now going to be k instead of I. So instead of I squared and I cubed, we're not looking for everything in terms of k. And think of n as it's like a number. So think of n as your coefficient, your constant. Okay. So I'm going to separate this. So I have 1 over n summation of k squared minus 1 over n summation of 1. Now notice my upper bound is in terms of n, so the best I can do is to represent my sum in terms of n. So I'm not going to be able to get a numeric value at the end. Everything should be in terms of n. So I know summation k squared is just going to be n times n plus 1 times 2n plus 1 all over 6. Right? Instead of summation I squared, the same thing as summation k squared. I'm just a different variable here. Okay, if I clean this up, do common denominator, I'm going to end up with 2n squared plus 3n minus 5 all over 6. Okay, bottom of the page. Limits as n approaches infinity. We know that if we're dealing with infinity, we're going to go back to limits because we're going to we're going to lead towards the idea of moving from approximation using a set number of rectangles to infinite number of rectangles. So we're moving in that direction here. We know that if we're doing limit as n approaches infinity, we compare degrees, right? We don't do direct substitution. I mean, we could, but then we do L'Hopital's rule and it just feels longer. It's just faster to compare degrees. We compare degrees between numerator and denominator. So example 5, let's say I want to find the limit of this expression. So if I clean everything up between numerator and denominator, I'm going to end up with n squared plus n divided by 2n squared. And we know that as n approaches infinity, we can just compare degrees. Degrees are the same. So we simply take the ratio of the coefficients. Okay, next up, page 10. what if we had to clean up the expression to get it ready before we can compare degrees? So if you look at example 6, we have to basically convert all of our summation i's in terms of n so that we can actually compare degrees in terms of n. I'll give you guys a minute, but then we can move on to page 10. Okay, so I do want to do limit as n approaches infinity, but that I is getting in the way. So I'm just going to multiply, see what that gives me. That gives me 4i over n squared. I know that 4 and n squared is just a coefficient constant. I can pull those out in front. And if I pull the 4 and n squared out in front, then I have summation I. We have a summation rule for that. We know summation I, if you look on the previous page, is n times n plus 1 over 2. Once you get everything in terms of n, then we can move towards comparing degrees. Clean all that up under one fraction. 4n squared over 2n squared. That's just equal to 4 over 2, which is so we're just going to continue adding more complexity to this process. What if we had more algebraic steps we have to do before we can get to the summation rule, before we can get to our comparison of degrees? So take a look at example 7. So example 7, we do eventually want to find the limit as n approaches infinity. We do want to compare the n degrees of the numerator and denominator, but we have to get the i's resolved. We want to apply the summation rules, but we can't quite do that yet because we have a bunch of parentheses, exponents in the way. So let's clean everything up first, separate each of our terms, decide what summation rules are in play, apply all those summation rules, and then we can do the limit of each term once everything is converted to be in terms of n. So I see a bunch of algebraic steps I got to do here. I'm going to take that 2 over n, push it in front. I'm going to FOIL out my binomial. Okay. Once I've FOILed out, I'm going to continue expanding the 2 over n through. My goal is to get rid of all the parentheses so I can see each of my 3 fractions, and each fraction will have its own summation rule applied to it. So I'm going to attach the summation to each of my fractions. And along the way, I'm going to push out anything that's not part of my rule as a coefficient. So summation of 2 over n, summation of 8i over n squared, summation of 8i squared over n cubed. I just want to isolate my summation 1, summation I, summation I squared, because those are the portions that can be applied to the rule. Anything that's a coefficient and n that can push out in front, those will just hang out. Once my substitution is complete, I can multiply those 2 over n, those coefficients back into my expressions. Okay. We know summation 1 is just n. Replace this summation with n. Replace this with n times n plus 1 over 2, and replace it with n times n plus 1, 2n plus 1 all over 6. And then now within each fraction, we're going to try to compare degrees. So this is 2n over n, my degrees match, so this will give me 2. For all of these, is n approaching infinity here. This is 8n squared over 2n squared, so this will reduce to be 4. This is going to be, now this one here, there's really no need. Okay, so I want to talk about a little bit of, we don't have to FOIL out this entire expression. Because all we care about from the numerator is what? The highest what? If we're doing n approaching infinity. It's the highest degree, right? So if I want to pick out the highest degree, I only have to worry about multiplying the first of each term, because every other term is going to be a lower degree. So this will be like 16n cubed plus, and then a bunch of lower degrees that it's not going to make a difference because we know we can ignore lower degrees. So once we can find the coefficient that goes with the highest degree, then we can ignore all the rest. Even, I mean, you could FOIL everything out, but once we can gather the highest degree term, that's all we need. So 2n over n, degrees match, highest degree is 1, so 2 over 1 is 2. My degree is n squared, so 8 over 2. My degree is n cubed, 16 over 6. Add all that together, and my sum is 26 over 3. Thanks. So we're taking step by step to kind of move towards what the area definition is going to comprise of. So we're doing all the algebraic step leading up to the definition. So I think we've alluded to this, but the idea that if we increase the number of rectangles for my subinterval, then we can continually improve our area approximation, right? The smaller our rectangle, the more gaps we're able to fill. So imagine increasing your rectangles in the same subinterval from 2 to 5 to 10. You can see that your rectangles, the more rectangles you have, the less gaps between the curve and the rectangles, and the more accuracy that we can expect. So that kind of begs the question is, well, how accurate can we get? Can we just continue to increase the number of rectangles? So the idea is, well, if we can continue to increase the number of rectangles, and if that improves our accuracy, what if we let n go out to infinity? Then technically, shouldn't we have the exact area? So that's the idea of that. If we push the number of rectangles out to infinity, then every change in the graph is going to be accounted for, and we're going to be able to arrive at the exact area under the curve. Okay, so now we're ready to introduce the limit definition, where we're going to push out the number of rectangles out to infinity. This is the definition for area. I think it helps if we can do approximation to kind of show how this formula is working. So just want to kind of talk a little bit about approximation first. Let's do like 3 or 4 rectangles and then see, how does this formula do its job in terms of getting all the information, adding up the infinite number of rectangles. So I want to talk about this diagram first. It says the area under the curve is represented by, so whenever you see, we're going to talk a lot more about how to involve this notation, but this is the integral notation. The integral notation is just basically showing that we're accumulating a function over a period of x values. So just like how we were talking about when we do area under the velocity graph, we're involving area. Okay, so this area component is this f of x times dx. It has that area component. We're essentially finding the area of some region between two boundaries. Right, so that integral notation right now, all you need to know is it's antiderivative, but it's area related. It's giving us some information about the area under the curve. So we're going to approximate this area under the curve. So we're going to approximate the area under this x squared plus 1. So the integral from 0 to 2 of x squared plus 1 dx. Okay, so all this means is I want to find the area under the curve, but we're doing an approximation, so we're going to do a squiggly line. Okay, so we're going back to approximation here. Now I want to do four subintervals. So remember we have a formula for width, right? So width is b minus a over n. So my a and b is 0 and 2. My n is 4. So 2 minus 0 over 4 is 1/2. Okay. So starting at 0, we're going to keep adding 1/2 until we reach our endpoint. So 0 plus 1/2 is 1/2. 1/2 plus 1/2 is 1. 1 plus 1/2 is 3/2. And 3/2 plus 1/2 is 2. Let's do left-handed rectangles. Okay. I'm just arbitrarily choosing that. Oh, sorry, this graph is showing left-handed rectangles. Sorry. Or left-sided rectangles. So we're gonna do width times height, right? So the first rectangle, what's the width? 1/2, okay. And then the height, how can we find the height? Plug 0 into the function, right? So I'm gonna let f of 0 to represent what the height is. And eventually we'll find the height. But first I just wanna show that function notation, right? So f of 0 will get us that y value, and that y value will give us the height. Plus 1/2, okay. What's the height? What's the height representation of my second rectangle? Good, f of 1/2, right? If I plug 1/2 into the function, that will give me the height, whatever that height is. Go down the line, f of 1, and then 1/2 f of 3/2. We don't go to 2 because 2 is not, we're not using the right endpoint, right? We're using the left endpoint. So now we get, I'll just find all these values for us. Plug in 0, we get 1. Plug in 1/2, we get 5/4. Plug in 1 into the function, we get 2. And then plug in 3/2, we get 13 over 4. Add all that up, our approximation is 3.75. Okay, so I want to use this to kind of explain how the definition is accumulating infinite number of rectangles for its role. Okay. Okay. Everybody okay with the approximation using 4 rectangles and the function notation? Okay, so this is what the limit definition is doing. Okay. You got 2 components here. You have the width component, and then you have the height component. Okay. Now, we've been doing approximations wise, we've been doing our width and height manually, right? The width was 1/2, and the height was continually changing. F of 0, f of 1/2, f of 1, f of 3. So here, the b minus a over n is finding that width. Now, it is leaving that n alone because it's going to eventually push that n out to infinity. For us, we let the n be a static value because we only needed 4 rectangle. But for the definition, it's gonna hold on to that variable n because it eventually wants to push that number out to infinity. Now, how do we find each of the height values that we want to plug in? What do we do? To get from 0 to 1/2 to 1 to 3/2, what do we do? We kept adding what? Right? We kept adding by the width, right? We kept adding by the width. Now we're doing that manually, but then if we're to put it into some formula to kind of get that engine to do it for us, that's what this is doing here. This A, f of A means it's starting at whatever the left endpoint is, and then this b minus a over n times I is basically going to keep adding the width over and over again to get to the next value, then plug in to find the height, and then it continues to increment. So this is the engine that is allowing this number to continue to increase. Now, we're not, once we plug everything into the formula, then the formula will do its job. We're not, obviously not going to be adding all these infinitely number of terms, but I just want to show you how this is doing its job. So it's all compacted into one statement rather than, adding infinite number of terms and showing all your width and height. So now we're going to use the definition and move towards, how do we find the area under the curve if we have infinite number of rectangles? So it's going to feel a little messy because we have to hold on to all these n values because we want that flexibility to change that number of rectangles out to infinity. So that's why it feels more complicated because we can't just rely on a single number and because if we rely on a single number, then we're sitting at an approximation. Okay. All right, so let's look at part B here. We're going to do the same problem, but now we're going to move towards finding the exact area under the curve rather than just an approximation using 4 rectangles. Okay, so above B here, I'm going to write I'm going to write the definition up here, and then I'm going to apply it step by step. Okay, there's my width component, there's my height component. Right, what are my A and B values? 2 and 0. So let's go ahead and do that. We can go ahead and replace all of our A and B values with 0 and 2, and then we can just continually update as we move forward. Oops, sorry, I left off the summation here. Let me put that summation back into my definition. So you said 2 minus 0, right? So 2 minus 0, that's just going to be 2 over n. So there's my width representation times f of a. What's my a value? 0. That's nice. That's just that can just drop out. Plus b minus a over n. So plus what? 2 over n. Yeah. So I'm just going to say 2 over n I. Now, we have this in function notation. We have to put this into our function somehow so that we have something that is actually, for this specific problem and something that will tell us the height at every moment on the graph. So we're going to replace every x with 2 over ni and get this out of function notation so we can begin to do the algebra and move towards, summation rules and finding the limits. So our next goal is how do we get this out of function notation, because we want to be able to algebraically merge some of these together. So this 2 over ni is going to replace the x in my function. So that's 2 over ni squared plus 1. So now this feels like the previous example where we're going to just clean all this up, get all of our terms to separate, decide how can we involve our summation rules, apply our summation rules, get everything in terms of n, and then do limit as n approaches infinity. Right. So from this stage on, it should feel like what we were doing here, cleaning all that up and getting it so that we can see all the summation rules begin to be applied. Okay, so beginning my cleanup process here. Let's continue to zoom in here. Oh, sorry. My bad. I should have squared this, so this should be n cubed at the bottom here. Okay, I'm going to separate into individual summations, and along the way, I'm going to push out any number and ends in front. I think once we're here, we should be able to identify the summation rules that's associated with each part. Now, I only care about the highest degree, so I'm not going to spend the time to FOIL everything out. We can just take the first term of each part and then a times n times n times 2n. That's 16n cubed. We know there are smaller terms, but lower degrees, but that's not going to make an impact on our limit. So this fraction is just 16 over 6. Second fraction is just 2 over 1. So 14 over 3. So we're able to find, essentially add infinite number of rectangles to find the exact area under the curve, which is obviously a lot more accurate than just using 4 rectangles. Okay, next page, page 12. So number one, we're just going to practice rewriting the definite integral using summation. We're not going to go all the way through the process, but just so we can get everything in terms of I and at least the first step of this process. I just want us to practice that. So we're trying to get into this form and try to get this out of function notation as well. So let's try that for number one here. Rewrite the definite integral using summation notation. So start off with your width. What's our A and B value? A is 2, yeah. And my B is 6, right? So the width for my problem is going to be 6 minus 2 over n, which is 4 over n. So 4 over n can replace all my B minus A over n. Oops, sorry. F of A, what's my A value? 2. F of 2 plus 4 over ni. So now this, everything inside the parentheses will replace the x of my function, right? So my function is x squared minus 3. So I need to put all this into the x, and then that squared minus 3 will replace this function notation. Okay, so let me show you what our last step is going to be. So there's my width component. And then here's me plugging my argument value into my function. The rest is just cleanup, but I want to able to get to this stage. After this, it's just foiling, cleaning up, getting all the i's in terms of n, using summation rules, and then eventually find the limit. Let's see here. Okay, let's just do one example of this one here. So this is these next few problems are kind of like what an AP exam question would be like. You'll never get an AP exam question where they're asked you to find the area using this process. It's more of, they will represent portions of this process and see if we can kind of work backwards or understand what the, how to interpret what's going on. So even though AP exam is not going to have this exact scenario, we do need knowledge of the process in order to answer some of these questions. So if you look at example 2 here, it says rewrite the summation notation as a definite integral. So basically, this came from this integral notation, right? So the idea is we can get from here to here, but are we able to get from here back to this x squared minus 3 or this integral notation? So let's talk about if this was given to us, are we able to go backwards and realize that it's coming from this? So here's the hint. The hint is that, well, I know my width is 4, right? B minus A is 4. And I know that my A value is 2. So in order for my width to be 4 and my A value is 2, my B value has to be what? 6, right? That's the only way that I can get a B minus A to equal to 4. So that's a little bit harder, right? To kind of work backwards into this process. You know that your B minus A is equal to 4. You know that your A is 2. So B minus 2 is equal to 4. B must be equal to 6. And if B is equal to 6, then that's how we know using these two numbers that our bound is from 2 to 6. Right? That's a little bit harder to interpret backwards. You know that everything inside the parentheses is going to be your x. So basically x squared minus 3 is going to be your expression. So that's how sometimes AP exam can look, where they give this to you and ask, hey, can you tell me what integral is associated with that process? So let's try it for this one here. So here, if my width is 6 and I'm starting at 4, what could be my bound for this problem? From 4 to 10, yeah. And this whole thing is just my x, right? So this is one way to represent it. There are other ways as well, but we can just focus on the easier one for now. Okay, so we'll stop there. No homework except to study for your quiz. Help session in the morning, 7:15. I'll send out a reminder on Sunday that your quiz is Monday. And focus on the topics that I highlighted on the front page of my packet. All right, come get your phones.
About this one?
Yeah.
Can you remind me how we went from this one to 60 and the cube?
So,
like,
yeah, like this.
I think I missed that part.
So I didn't want to end up boiling all this out because every other term is going to be lower.
Yeah.
I mean, I can.
You're gonna get. I think I'll make it worse.
These ends up being. But we're doing limit infinity, we only care about the height. So that's why I was.
Oh, so the difference
Yeah. Make sure you multiply all the coefficients associated with the height. That was.
Thank you.
I don't. They literally met every day. I actually. You said that mentioned it.
Okay.
The whole time, I
need the.
What?
I have a hundred of them right now. The easiest AGM.
68.